Okay, let's go to the next slide. It's a very important term. What is the neutron separation energy Sn? What I mean by Sn? Sn is the minimum energy required to remove one neutron from the nucleus. Okay, we have a nucleus of Zi and Ai. This is the initial nucleus. We have the initial nucleus of the initial atom, and we have the final nucleus of the final atom. Zi Ai, and the final will be Z final A final. Okay, if we apply this quantity of energy Sn to remove one neutron from the initial one. So initially we have Ai, Zi, and I. We apply Sn to create the final atom. The final atom has Zi, the atomic number. We have the uh, number of protons, Zi. It's the same like Z initial, because we don't change the number of proton. Just I want to take out one neutron. Only the number of neutron will be changed. Okay, so N final equals to N initial minus 1, but Z final equals to Z initial, and A final must be equals to A initial minus 1, because we reduce the number of neutrons. So finally, we get this atom with Ai minus 1 as A final, and Zi equals to Z final. And we have Ni minus 1 plus 1 neutron, the extracted, we remove this neutron. So finally, we have this expression between the initial atom and the final atom, and Sn applied to the system to remove one neutron. We can write, to calculate Sn, we can write the conservation of energy between the before the reaction and after the reaction. Here, so here we have the energy of the initial atom equals of the initial nucleus equals to m. Here we have m of the initial nucleus times c square. The energy Sn applied to the nucleus equals to the rest mass energy of the final nucleus plus the energy of this neutron equals to mc square. We can calculate Sn equals to mziai. Okay, anyway, we can put this one minus this one. Okay, we get finally mzfaf plus mn minus mz initial. A initial, we put a common factor c square. Okay, this is the general expression of one neutron separation energy Sn. We can say one single neutron separation energy. In general, you have to know this expression. I don't give you this, you have to know it. Now I ask you to find another expression. Show that Sn, which is equal to this expression, equals to the initial nuclear binding energy minus the final nuclear binding energy. You know, for each nucleus, we have a certain quantity of binding energy. Okay, the initial one, we have a initial, we have, it's here, we have a Zn, and the final expression will be a minus 1 Zn minus 1. It's the binding energy of the initial atom and the binding energy of the final atom. I have to find this relation. It's important to know how can we find Sn equal to the difference of binding energy of the initial atom and the final atom. Okay, first of all, you know, m, I want to find m, the nuclear mass of the final atom, and I want to find the nuclear mass of the initial atom. Okay, you know, the nuclear mass of the final atom, which has a Z proton and n minus 1 neutron, because we lost one neutron. In general, the mass of the nucleus equals to the mass of the individual nucleons inside. We have Z proton and we have n minus 1 neutron times mn minus the mass defect, binding energy of the final atom of the final nucleus divided by c square. You know, the final atom, I repeat, we have a minus 1, z, and n minus 1. We follow the same procedure to calculate the nuclear mass of the initial atom equal to z proton. We had n neutron minus binding energy divided by c square. We put the value of m final and m initial. We get this expression. Here we have m initial of, no, m final. We have m final, nuclear mass final, and here we have m initial. Look well here. Here we have ZMP, and here we have minus ZMP. Okay, we can cancel these two terms. Here we have N, N, Mn, and here we have minus N, Mn. Okay. Here we have minus Mn, and here we have plus Mn. Okay, times c square. So also we can cancel this term. Finally, we get binding energy. Also here we can cancel c square and c square, c square and c square. Finally, we get the binding energy of the initial nucleus minus the binding energy of the final nucleus. This is the new expression of the neutron separation energy. So here you have to know these two expressions. First of all, Sn in function of the nuclear masses of initial atom and initial nucleus and final nucleus, and Sn equals to the difference of binding energy between the initial atom and the final atom of the initial nucleus and final nucleus. Let's take now the second term. What is the proton separation energy Pn? Okay, it's the minimum energy required to remove from the nucleus one proton. So initially we have Zi Ai, and finally we will lose one proton. So we have Z final equals to Z initial minus 1. Okay, the number of neutron will not be changed. but the total mass number A will be the initial one minus 1. We follow the same calculation. Initially, we have this initial atom or initial nucleus. We apply this quantity of energy to remove one proton. Here we have the removed proton out of the initial nucleus. We do the conservation of energy between the initial state and the final state. The rest mass energy of the initial nucleus plus the proton separation energy equal to the rest mass energy of the final nucleus plus the mass energy of the extracted proton. We can calculate Pn equals to m nuclear mass final plus mass of one proton minus the nuclear mass initial times c square. Okay, the same example, I want to show that Pn equals to the difference of binding energy between the nuclear binding energy between the final, the initial nucleus and the final nucleus. Okay, initially we have mZn equals to Zmp plus Nmn minus the binding energy. Finally, we have mZ minus 1 and n. We lose one proton. So the total mass of proton equal to Z minus 1 mp. The total mass of neutron equals to n mn minus the binding energy, the nuclear binding energy, B divided by C square. Okay, we substitute the value of MF, M initial and M final. And we can cancel here, for example, we have ZMP, and here we have ZMP, minus MP plus MP times T square, NMN minus NMN, we get finally the initial binding energy minus the final binding energy. Okay. Also, you have to know these two expressions of Pn in terms of the nuclear masses and in terms of the binding energy.